Okay, now we will be doing energy in dielectric systems. We have in previous chapters done energy in normal charge configuration, like the total energy stored in any charge configuration is equal to the work done to bring that charge, make that charge configuration happen, right? So we have written this as half epsilon naught integral of E square d tau integrating over all space, right? Integrating over all space, we have written it like this before. Now this was when there was no dielectric system, so we will now try to use the same logic and derive it for if there is a dielectric system. So consider that there is some dielectric material of dielectric constant epsilon r, and there already there is a charge configuration such that you have a vector d, this electric displacement, and a corresponding vector E. Okay, तो अभी ऐसे सिचुएशन है कि एक डाइलेक्ट्रिक मटेरियल है जिसकी डाइलेक्ट्रिक कांस्टेंट एप्सिलॉन आर है, और अभी हमारे पास ऐसा चार्ज कॉन्फ़िगरेशन है जिसकी वजह से एक इलेक्ट्रिक फील्ड E और एक इलेक्ट्रिक डिस्प्लेसमेंट D है. नोट कि अभी मैं ये नहीं कह रहा हूँ कि लीनियर डाइलेक्ट्रिक है, तो अभी ये दोनों का लीनियर रिलेशन नहीं है, ठीक है. तो अगर मुझे एक और चार्ज लाना है फ्रॉम इन्फिनिटी, जो हमारा रेफरेंस है, टू दिस कॉन्फ़िगरेशन, मुझे कितना वर्क और करना पड़ेगा. सो डेल्टा W इज एक्स्ट्रा वर्क टू ब्रिंग अ चार्ज, लेट अस से रो एफ. मुझे रो एफ लाना है फ्रॉम रेफरेंस इन्फिनिटी टू दिस गिवन चार्ज कॉन्फ़िगरेशन. तो मुझे कितना वर्क करना पड़ेगा? जस्ट इंटीग्रल ऑफ रो एफ इंटू वी डी टाउ. V is our potential and rho d tau is dq, because ऐसे लिखते हैं कि this is equal to integral V dq, which is equal to integral V rho free d tau. Correct? Now we know कि rho free. Okay, one more thing. Why am I writing rho free? Because that is a charge I am bringing. I am controlling that charge, and that charge will stay there whether or not I put some external electric field. That charge does not depend on dielectric, right? So it is a free charge. So we know that del dot D is equal to rho free, right? Putting that here, this can be written as delta W is equal to integral of del dot D into V theta. Now del dot D into V. V is a scalar, is a vector, so it can be written as V into del dot D plus del of V dot D. Correct? So replacing del dot D of V vectors, fine. Del dot D of V, putting that here, we get delta W is equal to integral of del dot D V d tau minus integral D dot del V d tau. Note that you have minus del V, so I can change it as plus integral D dot E d tau. This I can use Gauss theorem and write it as closed integral over surface S of dV dot ds. This is integrating over V. Now if we integrate over all space, that is from that all the space that exists, this vector S is square. This is proportional to r square. This is proportional to 1 by r. This is proportional to 1 by r square. 1 by r square cancelling, but this is still 1 by r v. So this will tend to 0. So this term tends to 0 when you integrate over all space. So I'll write it so that you understand. All space this term tends to 0. So only this term remains when you integrate over all space. So we can write delta W is equal to integral all space d dot e d tau. Okay, now the problem is that we were bringing an extra charge here. So this rho f, what I have written, actually represents not the entire rho that exists, but only the extra free charge that I brought. So this d is just the extra electric displacement that has been created. Though everywhere I have by mistake written d everywhere, this d is actually only the change in electric displacement. My d, which I'll repeat just to clarify, it's my mistake. This d which I have written here and everywhere so far, this d is only the change in electric displacement that has been caused because I brought this charge. So actually this d is the change in total. This d can be, this is the change in total electric displacement. Correct? So this equation should actually have a delta d dot e d tau. Sorry for that mistake, I missed that. Right. So let us try and proceed from here. Okay. What more do we know? Now the problem is, to be able to write anything more, we need conditions. So the extra work done to bring a charge delta rho f from infinity to here is integral over all space the delta d dot e d tau. Right? Okay. The problem now is we cannot solve this any further unless we have any good condition given. That's all we can do. We don't have anything else. But if we assume that the material is a linear dielectric, so what we get is d equal to epsilon e, right? So we can write delta d dot e as epsilon delta e dot e, which is equal to epsilon half epsilon delta e into e delta e square, right? Which is equal to half delta of epsilon e in epsilon e square, which can be written as half delta of d dot e. Agreed? So let us try and replace that there. You will get half integral putting the delta out, because it really won't matter how you sum it up. So this is the extra work done. The extra work done to bring that charge from reference to given charge configuration is this much. So if you start from a zero charge configuration, your initial work was 0, so your final work will just be this value. So you can write work is equal to half integral d dot e d. Okay. You have your formula. I'll just add this note key. The derivation is not important. The max thing they're going to ask you is questions on this, right? So if you don't want to know the derivation, don't want to learn it, didn't understand it, forget it. ये फॉर्मूला रट लेना, जस्ट बाय हार्ट दिस फॉर्मूला, दैट्स मोर देन इनफ. इससे इसके अलावा इस पे क्वेश्चन नहीं आएंगे, डेरिवेशन तो नहीं पूछेंगे.